Good morning, ladies and gentlemen. Oh, look, the guys out there on the so Tuesday. I keep telling my kids Tuesday is grass cutting day, and I'm allergic to grass, and we cut the door on Tuesdays. We close the door on Tuesdays. Okay. All right. So sorry, distraction. Do this now. The human ear canal averages 0.25 meters in length, and that's small. Okay. And acts as a closed pipe resonator. Cool. How much of a standing wave could it hold? How long would that wave be? What is the resonance frequency? Do it, people. Pause the video. You got this.
You have a closed pipe resonator in your head.
0.025 meters? Is that right?
Yep. So think of it as the same as what we've been doing with these.
Okay. So how much of a standing wave?
Stop this and do it your own bad self.
Okay. Are we done?
We're done. We're ready. We're rolling.
Okay, so how much of a standing wave could it hold? Well, it's a closed pipe, so we know it holds a quarter of a wavelength, right?
So the length of the ear, so the 1/4 wavelength equals L.
That equals L right there. Okay. How long would that wave be?
Well, how do we get rid of the 1/4?
Let me actually write it like this. 1/4. No, we've never actually done it this way, but I mean, this works too, right?
Yeah.
So one wavelength is going to be equal to 4 times the length. That's number 2.
4 times the length of your, yeah.
Okay, all right, so what is the frequency? Let's see. We're dealing with this equation right here.
Yeah, and the speed of sound is 343 meters per second.
Like that, right?
Yep.
343 meters per second over our wavelength. Oh, I haven't calculated this yet. So 4 times 0.025 meters. Okay, so 4 times 0.025 meters, and I get 0.1. Okay, so 0.1 meters here at the bottom.
Yep.
And then 343 divided by 0.1, and we get
3,430.
3,430 cycles per second. So that is the frequency. Want to hear what that sounds
And
like?
we have a device here that has a frequency of just about that. Hear that? Here, I'm going to go all the way in the back of the room. Can you hear it back here?
Hopefully the microphone's picking it up.
It should be, because here's the thing. That's the resonant frequency of your ear. If you hit that really loud, it'll hurt.
Okay, and what's happening there? You've got a standing wave. Your ear canal is vibrating at just the right frequency. Waves are interfering with themselves at just the right frequency that you're forming a standing wave in your ear.
And that standing wave amplifies the sound. It increases the amplitude of the wave.
Yeah, right. Because remember when we were pulling it out at a certain length, it got really loud.
Right.
Right.
Yeah.
Okay, so right to revise. Okay, so you're not with me, but in your journals, this is what I want you to do. How can you measure the speed of sound with a tuning fork and tube and some water? Didn't we do this yesterday?
So do you know what you did?
Yes.
Do you understand what you did? So right or wrong, even if you're not sure, just write down. And if you need to cheat, if you need to pull out the lab sheet, go ahead.
Yeah, do it.
But in words, what did you do first, and then what, and then what, and then blah, 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 and how'd you come up with the speed of sound? So pause this and do it.
Okay, so big idea here is, what did we do yesterday to find the speed of sound?
That's right.
Okay. All right, so did you mention that we pulled the tube out of the water until we heard the loud sound?
That's an important part.
Then at that point, we measured the length of the tube from the bottom of the water to the top of the tube.
That's right.
Right?
That's the resonating length.
Now, we knew that we had to multiply that length of the tube by 4,
Yep.
because it's a closed pipe, in order to get the whole wave, the actual wavelength there.
Yep.
Now, we also did some extra adjustments, but that's not as important.
And then we had the frequency from the tuning fork.
We had the frequency from the tuning fork.
Oh, by the way, you're absolutely right. The adjustment isn't important.
Yeah, we want to.
It increases the accuracy of the results.
Yeah, And so we had the frequency, we measured 4L for the wavelength, and we found the velocity using this equation right here.
That's right.
Okay, it is important, but it's not important in our description here. Okay, so you good with that?
Yeah.
Yeah. Okay. All right. So conditions for closed pipe resonance: a node at one end and an antinode at the other.
And the reason for that is because one end of the pipe is closed, the other end is open. So you have one part of a standing wave at one end and another part of a standing wave at the other end.
Okay. So
There's equilibrium. Boy, you're getting good at these
I know.
standing waves, Ms. Mo.
watch out. I'm coming for your job. Just kidding.
You got it. What are you talking about? You're
I'm out here with my standing waves. Okay, so we've been talking about, let me do purple. I'll do blue. Okay, so we've been talking about a closed pipe. Wow, I missed that one, but that's okay. Okay, so a closed pipe, and we know that we said that has a node at one end, which is right here, and an antinode at the other, right? And so it's been a quarter of a wavelength.
because one bump is half a wavelength, two bumps is a full wavelength. So from the left to the right there, give them what one length would look like on the top. Put one wavelength from that first node to this third node.
From the first, so from here to here?
Yeah, up on top,
Oh,
up,
okay.
up
Like
above
this, like
everything.
this.
There you go. From there,
First.
there's half a wavelength, and you got to go all the way to there. There's a full wavelength.
Sorry,
So,
I got too many lines going
I know.
on here.
so that's a full wave. Put the Greek letter lambda there. There you go.
There we go. Okay. All right, so that's what we've been dealing with. We've been dealing with this guy right here.
That's
Okay.
right. So you have a node at one end, an antinode at the other.
All right, so, and now for something new. Okay, so what would happen if both ends were open?
Well, you got a pipe right here.
Yeah. Oh, and let's demonstrate with this. Okay, so we've been dealing with this, right?
No.
Okay, now what happens when both ends are open?
No.
Okay, so what is going on here? Let's talk about what's happening inside the pipe with the wave.
Well, first of all, you got a higher frequency. You get a higher
do.
pitch, lower pitch, and then higher pitch.
Okay, so that means if I get a higher pitch, that must means I might have a lower wave, a shorter wavelength.
Yes, ma'am.
So that means that I have more wave kind of smushed into here.
And why is that? Well, it's because you got the same situation at either end. One end is open and the other end is open. That means you're going to have
Ooh, okay. Wait, an open pipe resonator has the same parts in either end, a node and a node, or an antinode and an antinode. So what does that look like over here? So right here we've got a node and a node. So that means that we no longer are stopping here. Okay, we're gonna be stopping here.
you could draw your pipe on top for the open
Ooh,
pipe.
good idea. Okay, and now for this one.
And
Okay.
open on the other end too.
Now, I don't want this to be misleading. We're not changing length of the pipe here. The pipe is the same length, but we have more of a wavelength that's fit into that pipe.
Yeah.
Okay?
And there's an illustration in the book about this.
Yeah. Oh, perfect. Yeah, right here. Okay, so this is what we've been dealing with, right? We've been dealing with a pipe that was a closed pipe resonator, okay, and one end is closed and the other one is open, and we were holding our tuning fork up here.
Yeah.
Right? And we're getting that fundamental that resonance, right?
So you've got an antinode at one end and a node at the other end.
And how much of a wavelength do we have in here? A quarter.
1/4.
Right? Same exact pipe situation, but now it's open on both ends. So instead of smacking it down or putting half of it in the water, it's open on both ends, and that's why I touch it very quickly. And now I've got a half of a wavelength in there. So same size pipe, but we have a half a wavelength in there. Okay, and again, higher pitch. Okay, shorter wavelength.
You know, there's a demonstration you can do. You can blow across the end of the pipe. Put your hand over the one end.
Oh, right?
Yeah, and then blow. And then take it off. Ba-boom!
Okay, you guys hear that difference? Okay, so how much of a wave will fit in an open pipe resonator?
I think we've already answered that question.
We covered it, okay? And you guys might remember this. This was our closed pipe, right? In our closed pipe, oh, this is a great demonstration because the pipes are the same
Yeah.
length here. We have a quarter of a wavelength when it's closed on one end. Now it's open on both ends, and we have half a wavelength. Now it either could be a node or a node, kind of like how what we have over here, a node and a node.
Yeah, let's leave it at node or node. They have an antinode and an antinode here.
But don't confuse yourself too much here.
The main thing is you have the same parts of the standing wave at either end, regardless of whether you consider it a node or an antinode. And for the closed pipe, it's opposite parts.
Okay, the fundamental frequency for an open pipe resonator is a half a wavelength, and that's what's important. Half a wavelength.
Were we going to do something right here?
Let's see. We were. Okay, well, first I've got page 359, which I think we just talked about.
Yeah,
Okay.
you got this.
And then it says demo with open pipe. That's this guy right here, I think. Right? No, not yet.
Yeah, and let's find out what the frequency of that open pipe is going to
that's
be.
what we're going to do. Good job, Boykin.
I knew there was something we were going to do.
Remember like a steel trap. Okay. All right, so here is our resonator, okay? And we want to figure out what the frequency is.
Right.
Okay? And so what do we need to find the frequency? Let's look at our equation again.
Well, if we assume that the speed of sound is 343 meters per second.
Okay, if we assume that,
well, it's
then we just need the wavelength, right?
Okay, so we can measure the length of the pipe.
Okay, let's do that. I'm gonna put it right here on the ground, on the thing here. I'm gonna call it 0.35. That's what we had before.
Yeah.
Okay. So
0.35 meters.
Okay, do we want to do it? Right.
Well, 0.35 meters is half a wavelength.
That's half a wavelength. Now, so we have, it's an open pipe, so there's half a wavelength in here, but how long is the full wave? Double.
Double that. So 35 times 2 is 70. So that's going to be 0.70 meters is the entire wavelength.
Boom. Okay, so let's plug this in. Okay, 343 divided by 0.7, and I get 490.
Let's take that to the tone generator.
Take it to the tone generator. Cycle per second.
So this should be right about 490 hertz, 490 cycles per second. 490.
490. Hey, let me see if I can.
Pretty close. Pretty close.
Pretty close, not bad, right?
And why isn't it exact? Well, because there's that correction factor on the end.
Okay, so.
See how simple that was?
What two things?
Now something completely different.
Oh yeah, we're changing speeds here. Okay. So what two things determine the loudness of the sound that you hear? What two things? Hello. What is changing about hello and hello? Amplitude is involved.
It's the amplitude. It's the difference between the high pressure and the low pressure, between the compression and the rarefaction, between the stretch and the squeeze.
And if I'm right here, hi. Hi. Right?
Yeah, yeah.
Like why did I choose those words? I don't know.
Well, no, that's an important demonstration.
Yeah.
One thing is the amplitude of the original source, and the other is how close you are to it.
Yeah, further away it's going to be harder to hear. So those two things matter. All right. How do we hear the difference between a high and low frequency sound?
What do we call it?
Pitch.
That's
it's
right.
Pitch, right?
Yeah.
Okay. So difference in pitch. And so if you guys remember when the Boykinator was driving his truck towards me, how is what I heard different than what he hears?
When I was honking the horn, you heard something and that was different from me. What was different?
So I heard a high pitch,
Yeah.
right? Now I just heard a higher pitch than what you heard.
Yeah.
Okay, so how about when Mr. Boykin was moving away from me? So I would hear a lower pitch than what he heard at that point.
Yeah.
Okay.
Wait a minute. This sounds like review. Are we going to be taking a quiz pretty soon?
Soon. Stay tuned. Okay, so this is review. So as the van is passing by you, what happens to the frequency you hear?
Well, it goes from that high approach to the low afterwards. It does a.
Yeah. And so it goes from a high to low, right? That the frequency goes from a higher pitch to a low pitch. And so that is what you experience as it passes by. Okay, what is the Doppler effect? Dun, 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 dun.
Well, that's the change in frequency that an observer hears due to relative motion between the source and the observer.
That sounds like a very well worded response. You guys should write
Sounds
that
like
down.
something out of a textbook.
Sounds like something that Mr. Boykin has taught for you. Okay. So, what diagram would explain the Doppler effect? Let's do it. Okay. So we have said car. Okay. Okay, Mr. Boykin is in here. Okay. And then Miss Moore is over here. And which direction are we gonna go? We're gonna go this way.
Well, forward or not, reverse. Can't go as fast in reverse.
Yeah. We'll go this way. Okay. So sound emanates out like a bubble, right?
Right.
Okay. And so every single point, Mr. Boykin is blaring his horn here, and so sound is going to be emanating out of here like a bubble. Okay. And so.
But because, making a little circle.
The little one right here that we
Yeah, a
draw?
little
Okay.
tiny circle.
So little circle here.
But as it moves forward, the location of the where the wave was born moves. So you've got circles with different centers.
Yeah, because this is really moving forward,
Yeah.
right? And so what happens is, as the car moves forward, okay, the circles are changing. Running out of space over here, okay?
So what about the wavelength in the front?
Great question. So in the front, this is a very small distance, right?
Yeah.
So we have a small wavelength,
Yeah.
okay? How about in the back?
Well, it's farther apart.
Yeah. Okay, this is a very large wavelength.
Yeah.
Okay. Now,
Well, what about the frequency? What about the pitch you hear?
so here our frequency is really high, right?
It's higher than what the driver hears.
And then over here, yeah, higher than the driver here is relatively, and here it's really low.
Yep.
Okay. And so when I'm over here, this is Miss Moore, me, okay, with my hair. Okay, I'm experiencing a high frequency, and then as it passes, okay, she got her dress on today. Then it's lower. It's a lower frequency. And if you are, having a hard time remembering this, always go back to your equation. Okay, velocity. Let's do wavelength equals velocity over frequency. If you have a a big wavelength, you're gonna have a low frequency.
Low frequency.
Right? If you have a smaller wavelength, you're gonna have a higher frequency. And so you can think about it mathematically. Equations just convey
And
ideas.
another way to do that is the wavelength is 2 and the frequency is 10. 10 times 2 is 20. But if you switch them around and the frequency is 10, I beg your pardon, the wavelength is 10 and the frequency is 2, then it still adds up, multiplies out to 20.
Yeah, and so you can use
One
both
gets
different-
bigger, the other gets smaller.
Yeah, you can use both ideas to help you with this. So when I ask you about the Doppler effect, this is what I'm looking for.
Yep.
Okay. Okay. Ooh,
Okay, now-
let me go back here. So we have 2 tuning forks here, right?
Yeah.
Okay. We've got. Oh, this shit's on. Okay, so we've got this one. Okay, then you've got.
They both have the same pitch.
They are the same pitch.
And they're
Okay.
on a box that has one end closed and one end open.
Okay, so watch this. You guys hear that? Do it one more time. Whoop.
So you hit this one and this one was vibrating. What's going on here?
Okay, so I whack my tuning fork
Yeah.
and it starts to vibrate. That vibration travels down to the box,
Yeah.
which then vibrates the air in the box.
Yeah.
Yes.
Yes.
Now, because these two boxes work together, the air travels down through here, the wave propagates through, and then we have the same exact thing. The air molecules vibrate the box, and the box vibrates the tuning fork.
Yep.
Okay, and what's important to know is that these are at the same frequency. I'm hoping you guys can hear that okay in the video.
Yeah.
So yeah.
Do that again. Hit it.
Oh, that was
And
a
then
good one.
stop that one. Yep.
Yeah, okay. All right, so now, ow, okay. I'm gonna go ahead and add, that's really sharp.
Yes.
Add this mass, just make it, we're just gonna make this one a little bit heavier. And that's gonna change,
Well, now, if you hit it now.
oh yeah, let's go ahead. So we'll do this one again real quick.
No.
Okay, and then,
No.
oh, that's it's a little deeper, right? A little lower.
It's a lower pitch, and we're not getting the resonance anymore.
Yeah, so if I was to,
The other one is,
it doesn't follow through.
yeah.
Okay. So let's go ahead.
What happens if you hit both of them now?
Yeah. Oh.
Wait,
let's try that one more time. Okay. Okay, so you guys hear that? I hope you can hear it. Sometimes I get nervous that it doesn't show up on the video. What I have noticed is sometimes the light stuff doesn't show up. But anyways, okay, so we are talking here about beats. So beats occur when waves of slightly different frequencies interfere with each other, and so without added mass, they are the same.
You know,
Same frequency, and then when I add this mass, the idea here is that they just have different frequencies.
and why does this have it? Because it has more mass, it vibrates more slowly.
Inertia, baby.
So you've got
Resistance to change in motion.
higher pitch, lower pitch. Hit them both at the same time. That is called beats.
Beats, baby. Not the kind you eat, but okay. I like beats. Okay, so here is a lovely. That's enough. Okay, a lovely little diagram we have here, and so we have a wave, two different frequency waves here.
Yep.
Okay, we've got the blue one and the red one, and let's go ahead and see what happens if we were to add these up algebraically, right?
Yeah.
This and this would cancel each other out.
Got a crest and a trough.
Okay, destructive interference, and then we come down here. What do we have?
We've got looks like a node.
Node, yeah, like nothing, right?
Yeah.
The node is where
They
we get
cancel each other out.
Now let's go right here. Well, actually, yeah. Let's go right here.
Yeah.
They both work. Okay. So now we've got addition, right? These are both added
crest
together.
and a crest.
And I come down here, and you see we have a constructive interference down here. Okay.
So what we've got is you got a blue wave and a red wave that have slightly different frequencies, and sometimes they're right on top of each other, and sometimes they're opposite. When they're right on top of each other, you get constructive interference.
And you could go through and you can see where these cancel each other out. As
Destructive
right here.
interference.
Okay, we've got
Constructive interference.
but
and
on the
then
bottom side.
destructive interference. So
Yeah.
this is
how these
what's
sound.
going on.
So oscillating, these words are important. This is a great job describing what's going on. Oscillating between constructive and destructive interference makes a wah 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 sound. Okay, so that's what we have here, oscillating between constructive and
You could think that this is the blue one, this is the red one. And what you're getting is, if you go back to the previous slide, you have large amplitude loud, small amplitude soft. So this wah, 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 wah,
Great
wah.
playbook, and I pretty much that, okay? Bada boom, okay, we feeling good? How fast the wah 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 wahs are depend on how close the frequencies are.
Is this where we use the tone generator?
We're gonna go to we are going to
Oh,
look at this one,
yeah.
right?
Thank
Okay.
you.
Okay, so here we have 100 cycles per second and 120 cycles per second. So
Which
this
has a
one-
longer wavelength?
So this one's gonna have a longer wavelength.
Lower frequency, longer wavelength.
Yeah, this one has a higher frequency and a shorter wavelength. And if you don't remember the relationship between frequency and wavelength, you can also just look at these ones are a little bit further. Okay, these ones are a little closer, but
Yeah.
you can see that this one is a higher frequency, so less wavelength. Okay,
So what you got over on the left, you got that first crest, and
right here?
yeah, well, in the 100 you got a crest, and the 120 you got a crest.
Yeah, so
You
these
get
add up.
constructive interference.
And then let's talk about this area right here as we move through. Now we have a crest meets a trough, and those two are going to
Cancel each other out.
cancel each other out. And what do we have here? We have that
Destructive
that
interference,
quiet
like a-
destructive
yeah.
sound. Okay. Now, what were we going to do here? So we've got our demo. Oh yeah, we did that part already. Okay.
So what it has here, this is, since it's 100 and 120, it has the time between one watt to the next watt is 0.05 seconds.
Could we figure out? I mean, we could technically figure out what the difference between these.
Well, I
said-
think, isn't that the next
I
slide?
think it is. So we have this equation, right? This equation for beat frequency. What would be the frequency, the beat frequency here? And all that you have to do is take that first frequency and subtract the second frequency from it.
Yeah, so we had 120 minus 100 would
Okay.
give us 20.
Okay, so that would be the beat frequency.
Yeah.
Right?
And so it'd be 20 beats per second. That's 20 beats per second. That's a frequency. And it gave us the period in the previous slide, didn't it? Right here,
yeah,
it's
it
0.0. So 0.05. What's 1 over 0.05?
1 divided by 0.05. All right, so we got 1 divided by 0.05, but we get 20.
20. So the period is the inverse of the frequency, so that works.
Okay. Now, Boykin, we were going to.
We're going to use a tone generator.
Yeah, we were. Okay, so let's hop over here. So let's explore our tone generator. So this one is 257 beats, right?
So let's try 260.
Okay, so 260. So 260. I'm gonna go ahead. I'm gonna play this. Can you guys hear it?
I hope so. Yeah, they should
it's a
be able to
very
hear
gradual.
that. Now
Okay.
go to 270.
Let's do 270. Ooh, it's like oh.
That is much faster. Go to 265.
265. Okay, here we go.
All right, so
Oh, you
what
can
we're
definitely
hearing
hear
is we're taking, if this is 257 minus 265, that's how close. Do like 259.
259. Okay.
Hear how slow that is? See, we're getting closer and closer.
Yeah, it's
If you
like
do 258,
ooh. Stop. 258. Can you guys hear that gradual?
it's even slower. And then if you get to 257, with
If
any
you do
luck, there
exactly-
should be nothing. Ba-boom!
Nothing.
Zero.
Oh, yeah. It all sounds the same, right?
That's right.
Okay. All right. So, oh, are we on homework? Let me make sure there's something. Yeah, I think that's it. Okay. Let me double check that paper. Yep, that's it. We're good. Okay. So for homework, you're going to calculate the frequency of this pipe, and I've measured it for you. It is 0.46 meters.
We did this before with 0.35.
Okay.
So what frequency is the, is it open or closed pipe?
It's opened. Okay. Oh, what did I say up there? Oh no, I need to add that in there. Calculate the frequency of the 0.46 meter open pipe.
Close.
Close.
There you go.
Open.
Okay.
And then also read chapter 15, page 364 through 366. Do number 10 on page 367.
It'll be fun.